So now we're going to consider the third basic case where we have trigonometric functions on the right side of our equation. For this one, I want to start kind of in a backwards way, and let's just look at functions that involve linear combinations of sine and cosine function. But in this case, we will look at sine and cosine functions that have the same value of c inside. Now these values, if you remember what the sine and cosine functions are, they're just kind of periodic wave functions. So changing this number c just changes the frequency of that wave, how often it oscillates up and down. So sine and cosine functions arrive naturally in problems where things are oscillating and moving up and down, and we'll see that later. But for our purposes right now, if you have a function of this form and you differentiate it, it's going to be another function of this form. It's just going to have different constants in front of the cosine of cx term and the sine of cx term. So when I differentiate, for example, this a cosine cx, what I'm going to get is c times a times sine of cx, but then I also get a minus sign, because when you differentiate cosine, you get a minus sign. But anyways, it's a constant times the sine of cx. And when I differentiate this, I'm going to get a constant times the cosine of cx. So after differentiating, I still have a linear combination of cosine of cx and sine of cx. And this happens for the second and third, fourth derivative. This form maintains as you differentiate such a function. So this is what's telling us what to do when we have a trigonometric function or a multiple of a trigonometric function on the right side of our equation. So in this case, we have our linear differential operator L of y is equal to this phi of x, which is a multiple of a sine of 3x. So the guess solution that we should make is a linear combination of cosine of 3x and sine of 3x, where a and b are the undetermined coefficients that we have to figure out. We do that in the same manner that we've done in the last two cases. We take this guess, we compute the derivatives that we need to, we plug those into the whatever L of y is and set it equal to 2 sine of 3x. We're going to do a bunch of algebra to regroup it in terms of a cosine of 3x term and a sine of 3x term. The coefficient that's going to be in front of the cosine of 3x term in this case we'll set equal to 0, because phi of x doesn't have a cosine of 3x term. And then the coefficient we see in front of the sine of 3x term, which is going to be something involving a and b, we're going to set that equal to 2 because we do have a sine term here. So that's really the same idea we've been doing, just we have to deal with trig functions, so the equations look a little different. So if we have a cosine, we do the same guess. If we have a linear combination of two trig functions, cosine and sine, that have the same frequency, so cosine x, I have sine x, so c is 1 in this case. As long as they're the same, I make this guess. So let's look at an initial value problem and just go all the way through this. So step 1 is always find the solution to the homogeneous equation, or y sub h. So we look at the characteristic equation, we see that it has a repeated root, so we know what the form is. Again, this is stuff we just got done doing this, so you do this, whatever case this is, you're going to get two constants, c1 and c2, for this general form of the solution to the homogeneous equation. Next, we find the particular solution that actually solves our equation here at the top. This is where we're using the method of undetermined coefficients. Since we have a cosine of 2x, we're going to use that general guess that we said, a linear combination of the cosine of 2x and the sine of 2x. So a and b are the unknowns. So what do? We plug those in. Plug y sub p into this expression, and then set it equal to cosine 2x. So I want to do this, kind of talk through this a little bit, but there's a lot of little algebra to do here. I'm not going to show you every algebraic step, and we'll talk you through it. We're going to get two terms when we're done, because we know this from what we just discussed. We're going to get a cosine of 2x term, and we're going to get a sine of 2x term. So where is this cosine of 2x term going to come from when I perform all this differentiation of this function? Well, when I differentiate this term twice, I'm going to get a cosine of 2x. But I'm going to get a factor of 2 is going to come out twice from the chain rule. And when the first time I differentiate the cosine, I'm going to pick up a negative. So that's where this negative 4a comes from. Where else do I get cosine of 2x? When I compute one derivative of this. But one derivative of this is 2b cosine of 2x. But one derivative comes from the second term, which has a factor of 10. So that's where the 20b is coming from. And then the last place we get a cosine term is just from the 25y itself, so 25 of these, so 25a. I'm just regrouping that. So once we regroup our algebra, the cosine of 2x term has this coefficient, which we can simplify, and we will in the next step, as 21a plus 20b. We do the same thing for the sine of 2x term. Differentiating y sub p, the second derivative of this sine is going to give us a sine of 2x as well, but what's the constant in front? Well, we're going to differentiate twice, so we pick up a minus sign, and we're going to pick up a factor of 4. So that's where the negative 4b comes from. One derivative of the cosine will give us a sine. So that's going to be a 2 is going to come out, 2a, and a minus from differentiating cosine to get sine. And then we have this factor of 10. So that's where the minus 20a is coming from. And then the last place we get a sine of 2x is from the last term, 25y. So we just have 25 times b, sine of 2x. So that's where this coefficient comes from. And we're just regrouping it to rewrite it in this general form. Constant times cosine 2x plus constant times sine 2x. So the idea is this entire expression, we have to choose numbers a and b to make this entire expression equal to phi of x. The only way that can happen is if this number here is 1 and this number here is 0. So those are our two equations. So simplifying the algebra, these are the equations we get. Again, solving the system, we get the values of b and a. So we just plug those in, and now we have our particular solution, and we have our general solution for our entire problem. Y. Y is the sum of y sub h plus y sub p. Y sub h we got in the first step, and then the method of undetermined coefficients allowed us to determine what y sub p is. Again, the only place we have undetermined information is in y sub h. But we have to construct this general form for y first before we apply the initial conditions. So we have our solution, our general solution, and our two initial conditions. So again, all we're doing is solving a system of equations. We have a condition for y of 0 equals 1, and we have a condition for the derivative of y. So we're going to need to compute the derivative of y. Again, the first term is differentiating the first term from y. Stuff in parentheses here is from the product rule from the second term of y. And then the third and fourth terms are just by differentiating the third and fourth terms from y, using rules for trig functions and using the chain rule, because there's a 2x on the inside. So y of 0 equals 1, what does that mean? Well, this term becomes c1 because e to the 0 is 1. This term becomes 0 because there's an x there. The sine term also becomes 0 because sine of 0 is 0. And cosine of 0 is 1. So this really simply, it becomes a very simple equation. And in this case, it actually tells us exactly what c1 is without having to do any extra work. Now we go to the second condition. Y prime of 0 is negative 1. Do the same thing. Plug in 0 for x. So we let y prime be negative 1. And then we plug in 0 for x here. Again, we just see what that means. It means we get a negative 5 times c1. This term is going to be 0. So we're going to get a plus c2 from this term. This sine term is 0 because sine of 0 is 0. And cosine of 0 is 1. So we're going to pick up a 40 over 841. So negative 1 is negative 5c1 plus c2 plus 40 over 841. But we already know what c1 is, so we plug that in, and then we solve for c2. And reduce the fraction. Again, use a computer to do this, it'll reduce the fraction for you. So now we have everything, so we have our unique solution to the initial value problem.